Okay, continuing on with vector equations, and we have on page 32, number 9 asks, okay, to write this system of equations in terms of a vector equation. And so we have, in this particular case, all right, so we're going to have three weights with x of 1, x of 2, x of 3. And since we have three weights, okay, this is indicative that we're going to have three distinct vectors, and we have each equation set to 0. Well, I guess you can say we'll have in a way a fourth vector, which is going to be the 0 vector, and just writing what we have in terms of a vector equation. Okay, so all right, so we have with x of 1, okay, there's a missing element from the first equation. Okay, so we don't have an x1 term, so you have 0, and you have plus 1x of 2, 5x of 3, we have is equal to 0. And if we go row by row and fill in for each single vector, okay, so you have x1, you have 0, 4, negative 1, plus x of 2, 1, 6, 3, plus x of 3, 5, negative 1, negative 8, and we have equal to 0 throughout. Okay, so this will be our vector equation. All right. Now, for what we have in the case of number 11, okay, and it asks to determine if B is a linear combination of A of 1, A of 2, and A of 3 given what we have for A of 1, A of 2, and A of 3, and we have assigned for B, we have the vector 2, negative 1, 6. And okay, so if it is such that, okay, what we have here is going to be a linear combination of what we have for A of 1, A of 2, and A of 3, and rewriting what we have in linear combination equation terms. So we're going to have let the weights be x of 1, x of 2, x of 3, whereupon we have x of 1, A of 1, plus x of 2, A of 2, plus x of 3, A of 3 is equal to B. And okay, so again, putting each of A of 1, A of 2, and A of 3 in vector notation. So we got x of 1 plus x of 2 plus x of 3 times their respective vectors equal to b, which we have at 2, negative 1, 6. And as we squeeze what we have on the left-hand side, okay, and write as a system of equations, okay, so if you notice we have negative x of 1, we don't have an x of 2 term thanks to the 0 from this particular vector, and then we have plus 5x of 3 is equal to 2. And going row by row, we have 2x of 1 plus x of 2 minus 6x of 3 is equal to negative 1. And okay, now we don't have an x1 term for the last equation in the system, but we do have 2 times x of 2 and 8x of 3 is equal to 6. And we set this up as a 3 by 4 matrix. Okay, and we have in the makeup, okay, so I have negative 1, 2, 0, 0, 1, 2, 5, negative 6, 8, and again I have 2, negative 1, 6, and progressing toward reduced echelon form. Okay, so I want to make the upper left hand corner value as a positive 1. So I can do this by taking the additive inverse of the first row elements. Okay, so I have 1, 0, negative 5, negative 2. Now, I want to make the first column 1 at the top and 0 is at the bottom. Now I have, as well as the middle. Now I've got 0 at the bottom, but I want to convert this 2 to a 0. So in the interaction, if I go from 2 to 0, and I need 2 and a negative 2. So I can take negative 2 times the first row and apply to the second row. So we have R2 minus 2 times R of 1. And so I have 2 minus 2 is 0. 1 minus 2 times 0 is still 1. And we're going to have negative 6 plus 10, which will be 4. And then we're going to have negative 1 plus 4, which will go to 3. So this is what we have in the adjustment. Okay, so we have 1, 0, 0. Now for the next column, I have 0 and 1. Now I need to make the bottom row such that, okay, this 2 becomes a 0. Okay, so again, we have our pivot positions, upper left hand corner 1. Now we have the middle 1 located in the second row, and if I convert 2 to 0. So for what we have here, I'm going to convert this 2 into a 0. So I'm going to take the third row and take away twice the second row. And so for what we will have here, okay, we have 0, 0, 2 minus 2 is 0, 8 minus 2 times 4 is 0, and 6 minus 2 times 3 is also at 0. So we have 0 row, and it's going to follow that. Okay, last row we have 0 equal to 0, and that is going to be true. And just looking at what we have with the weights, we have x of 1 minus 5x of 3 is equal to negative 2. From the second row we have x of 2 plus 4x of 3 is equal to 3. And of course x of 3 is going to be free, okay, since we don't have a pivot location, okay, in reference to x of 3. All right, so it's going to follow that, yes, okay, B is a linear combination. And for the solution set for the weights, okay, so we have x of 1 equal to negative 2 plus 5 times x of 3. X of 2 is equal to 3 minus 4 times x of 3. And again, we have that x of 3 is free. Okay, now for what we have in number 26, okay, we have a column vector, or in this case with B, where we have 10, 3, and 3. And we have with A, we have a matrix that is comprised of 3 vectors, A of 1, A of 2, and A of 3. And we have 2, negative 1, 1, 0, 8, negative 2, 6, 5, 1. And we're going to have for W, okay, that would be the span of A of 1, A of 2, A of 3, which in linear combination terms, we have x of 1, A of 1, plus x of 2, A of 2, plus x of 3, A of 3. And for what we have in part A, it asks if B is in W. Okay, so we can take the linear combination from W and set equal to B. And once we translate what we have in vector and matrix terms, okay, so we have x of 1, again your A of 1, you have 2, negative 1, 1, and we have x of 2 times A of 2, x of 3 times A of 3, and again we have with B, we have 10, 3, and 3. And okay, now just writing what we have as a 3 by 4 matrix, going ahead and doing this. So we have 2, negative 1, 1, 0, 8, negative 2, 6, 5, 1, and 10, 3, 3. And again, just putting in reduced row, or I should say reduced echelon form. We're going to take half of the first row. So we have 1, 0, 3, 5. The other 2 rows remain the same. And if I convert, okay, the negative 1 and the 1 from the second and last rows respectively, so I'm going to add the first row to the second and deduct the first row elements from the last. Okay, so we have this particular set of values. Okay, so we have our first pivot position, okay, in the upper left-hand corner. Now we're going to have the next pivot position will be with the first 8 that appears in the second row, and I'm going to convert that to a 1. So I would take 1/8 of the second row. So we have 0, 8, 8, 8 becomes 0, 1, 1, and 1. And leaving everything else the same. And okay, so for the reduced row form, I have the desired 1, 0, 0. Now I want 0, 1, 0. So this negative 2 has to be made into a 0. So I can take what I have in the last row and add twice what we have in the second row. So if I follow through with R of 3 plus 2 times R of 2, I'm going to come out with this particular 3 by 4 matrix. So we have 1, 0, 3, 5, 0, 1, 1, 1. And again, we have zeros throughout. And we have that 0 is equal to 0. And just moving along here. So 0 is equal to 0 is true. So we have yes. We have that the vector B is in the span of A of 1, A of 2, A of 3. So B is in W. And regarding the weights, okay, so we have, again, you have x of 1 plus 3, x of 3 is equal to 5, x of 2 plus x of 3 is equal to 1. And since there was no leading element in non-zero form in reference to x of 3 is free. and we have thus the solution set for the weights. We have the x of 1 is equal to 5 minus 3x of 3, x of 2 is equal to 1 minus x of 3, and again we have the x of 3 is free. Okay, now we have for part B, it says to show that the third column of matrix A is in W. And again, so we have with A, okay, we have a 3 by 3 matrix, and the third column is going to be in reference to the vector A3. And for W, again, that is the span of A of 1, A of 2, and A of 3. And we have x of 1 times A of 1 plus x of 2, A of 2 plus x of 3, A of 3. And among the infinitely many linear combinations we have for W, one combination will be setting x of 1 and x of 2 to 0 and x of 3 to 1. So if I have setting both x of 1 and x of 2 to 0 and a of 3 equal to 1, and we're going to have for the outcome, okay, so you have 0 times a of 1 plus 0 times a of 2, and of course you have 1 times a of 3. Okay, so we have from the span, okay, we have the first two set of terms to cancel, and it's going to follow that out of all the possibilities we have in W, that a of 3 is one such existence.